All right, Calc 12ers, here we go. Not a nice day today, kind of overcast, really green out, but that's the way she goes. And let's roll. We're going to be looking at the second derivative test. So we're in chapter 5, kind of in the midst of learning concavity and points of inflection. Now we're going to talk about a test that uses the second derivative, and it's 5.4 in the textbook. All right, here we go. A few things to remember. Just do not get confused today with the last lesson on second derivatives. The second derivative by itself gives you concavity and point of inflection information, which is really important from a point of view of just extra attributes to the graph of the f of x. The second derivative test, though, it does something that we already can do. So I find today a little redundant, but it's nice to know it, just an extra tool in your tool belt. It's another test to determine maximum and minimum values of f of x. So here's the theory behind this. Let's assume you have a minimum value here, which you would easily be able to find with your first derivative by going, oh, I'll take the first derivative, where does it equal 0 or undefined or endpoints, and then I could see if it goes from negative slope to positive slope. Oh, it's a minimum. That's your first derivative test. The second derivative test is this. You, first of all, take your first derivative, find out the critical numbers, and if you know there's a critical number at C, you know there's going to be a max or a min there or neither. If you take the second derivative, though, and plug the critical number into it, if you get a greater than 0 second derivative, that tells you it must be concave up. And if you have concave up with a critical number that was equaling 0 for the first derivative, you know it has to be a minimum. All right? So it kind of avoids the number line first derivative test, but it does involve you taking a second derivative. So in math, usually where you steal work somewhere else, there has to be work goes in elsewhere. So there's never always a silver bullet to make the questions easier. The other scenario could be you have a maximum here, which you would have known with your first derivative test, but the second derivative test would be, okay, you know there's a critical number there. You know there's a critical number making the first derivative equal to 0. You then plug that critical number into your second derivative, and if you get a negative, you know it's concave down, and concave down with a slope of 0 must mean a maximum at that C value. So that's what the second derivative test is, ultimately. Why I don't like it, I'll show you some examples of why I'm not a fan of it. Here's 3 examples of why I do not like the second derivative personally as a tester. Let's say you had a situation like this, where you had a first derivative had a maximum there because it was a does not exist situation, and it went from positive slope to negative slope. You'd know right away if it existed there, that's a maximum. But the second derivative, if you use the test exclusively, you would not get any information from this, because the second derivative would also not exist, because the second derivative will not exist at the same place the first derivative won't exist. So if you get this situation happening, the only way to figure out whether that's a maximum is to do the first derivative test anyway. So the second derivative test is useless. Same thing here. Here there's neither a max or a min. First derivative and second derivative won't exist. Again, second derivative test doesn't tell me anything. I'd have to do a first derivative test to see, oh, it's really neither, because the slope went from positive to positive, no change in slope. So it must be a neither, max or min. And then my favorite, the one that's kind of the most duping, is let's consider like y equals x to the 4th. First derivative is 4x cubed, so the derivative is 0 when x is 0. We know from the picture, obviously, there's a minimum there, but let's say I didn't have the picture, and I had my second derivative. Second derivative would be 12x squared. If I plug the critical number in of 0 here, I get 0 out. And if you get a second derivative equaling 0, that doesn't tell you anything about concavity at all. Maybe lead to a point of inflection, possibly, maybe not. That tells me no information. So right there, if that was a test alone, I'd be like, I don't know. Is that a max or a min? Like, unless I had the graph, but the first derivative would tell you. So second derivative test is not helpful here, so you must use the first derivative. So that's why I find today a little redundant, but we'll go through 2 quick examples, and that'll be it for today's little lesson. First example, now the only time I must admit I do like the second derivative is if it's a polynomial. Then the second derivative is so beautiful unless you get into a situation like this, and if you do, it's just really unlucky. All right, so find the max and min value for this function, this cubic, using the second derivative test. So here they're forcing you to do the test. So it's like, okay, I'll do it. I can take the first derivative in my sleep, 3x squared minus 12. I can take the second derivative also in my sleep because it's a polynomial, get 6x. To do the second derivative test, first thing you need to do is you need to find the critical numbers. And the critical numbers always come from the first derivative. Remember, 3 places. Where does it equal 0? Where is the derivative undefined? And are there any endpoints? So a nice review of old skills. Where does this equal 0? So where does 3x squared minus 12 equal 0? Move the 12 to the other side, divide by 3, x squared equals 4. So the 2 critical values out of that would be x equals plus or minus 2. So I have 2 critical values that I'm going to be interested in. Are there any does not exist? Nope, there's no denominators or square rooting negatives or logs. No endpoints, so none, none. So I know my 2 critical numbers. So 2 critical numbers are x equals 2 and x equals negative 2. So the second derivative test would literally be this. Second derivative test. I would literally go to my second derivative and plug 2 into it. And I should be able to do it again at my sleep. 6 times 2, 12. Multitask, plug in the other critical number, negative 2, get negative 12. So what does this tell me? My second derivative is positive. A positive second derivative tells me it's concave up. If I have a critical number where the slope is 0 at 2, I know the slope is flat and it's concave up. Therefore, f of x has a minimum at x equals 2. And what is the minimum if they want the actual minimum value? So minimum x equal 2 of f of 2. So I can go and plug 2 in to get that value. So 8 minus 24 plus 5 and get my number. Next piece, when I plugged in negative 2, the other critical number, got a negative second derivative. Negative second derivative means concave down. Concave down with slope 0. F of x has a maximum at x equals negative 2. And what's the maximum value? Maximum value is f of negative 2. There's not an at there, sorry. So minimum at x equals 2 of f of 2, maximum at x equals negative 2 of f of negative 2. Which we would have known anyway because we know cubics, positive cubics look like this. We would know the first value there at negative 2, that'd be the max, that'd be the min. We could have known that instinctively, but this is just showing you the test. That's the only time I find the second derivative nice. So I actually know max and min without having to do a number line test. I like the number line test, so personally the second derivative kind of steals me of my fun. Okay, last example, and this is the only time I really don't like the second derivative test because it means when you have ugly functions, the first derivative alone, I'd urge you to practice that. That's going to take some people, depending on your skills, that could take a while to get to there. That might take 5 minutes just to take the second derivative. Then it might take another 5 minutes to take the derivative of that to get to there. So not new skills, just laborious skills. So there's the function. First derivative, second derivative. I've done that already because that's the longest part of the question. That'll be 90% of the work right there. 80% for sure. So once you've done the first and second derivative, notice it didn't say to use the second derivative here, but I'm going to use it just for the sake of the question, but I don't have to. If I want max min values, that guy could do it all. Okay? So, critical numbers. First step. Where is the first derivative equal to 0? For a rational function, it'll always be where the numerator equals 0, and right away I can see that's x equals 4. So there's a critical number that I'm going to have great interest in. Another critical number will be where the derivative does not exist, and that in this case would be where the denominators would equal 0, and it's already factored nicely, so I can see that you could have x equals 0 and x equals 6 are potential critical numbers. And then I got to think about endpoints. Now there's no excuse me, endpoints built in, but are there any like square rooting endpoints or points of where the graph ends? And I go to the domain. This is your cube rooting something. This is cube rooting. You can cube root negatives and positives. There's no denominators, so it's all real numbers, so there are no endpoints, which just means all of those are potential candidates. All right, now again, for me, I would have stopped there. If they wanted max and mins, I would have just number lined it up. And here's the irony of it. I might have to do this number line anyway, because this guy might not tell me any information. So let's hold off on this, even though I would probably do this anyway. So let's just take a look at the second derivative at these critical numbers. So the second derivative at 4. If I go and plug 4 into this, I don't feel like, I just need to know whether it's positive or negative. I don't care about the value of it. So the numerator is negative. I'm cube rooting something and then fourth powering it. It's going to be positive no matter what, because I'm fourth powering it in the end. So that'll be a positive times, and if I plug in 4 here, that's positive. So this will spit out a negative. So that was a 0 slope at 4. So I know the slope is 0. Second derivative is negative. That must mean concave down. So if it's concave down with a slope of 0, you must have a max at x equals 4. So thank you, second derivative. You actually saved me a little bit of number line trouble. But second derivative at 0, I have negative on top. Uh-oh, undefined. So if the second derivative does not exist, and yet the function and the first derivative exists there, this tells me no information. I don't know. Thank you, second derivative, for not helping me. Same thing with the second derivative at 6. This gives you 0. So you end up with it does not exist again. So then here's where it's kind of like, this is concave down happy face, so to speak. Sorry. Sad when you laugh at your own jokes, isn't it? Anyway, okay, so I have to do the first derivative test anyway. So I was like, okay, all that work to find out very little. So I know 4 had a 0. I know 0 had undefined, 6 had undefined. Now I have to test all these intervals. Oops, it's a first derivative because I'm doing a first derivative number line test. Man, what a pain. Okay, so I would plug in here, I don't know, -5. Here I'd plug in 1. Here I'd plug in 5. Here I'd plug in 10. So first derivative at a -5. Numerator is positive. Cube rooting a negative, that's negative. That's going to be a positive, so positive, negative, negative. This gives me a negative. So I know it's negative slope. The graph's going down, decreasing. Plug in 1, so I got positive, positive, positive. So I must have, there must be a minimum at 0. First derivative told me that. This told me nothing. At 4, so at 5, sorry, negative, positive, positive, so I got a negative. Now we already knew that. There's the concave down part that we figured out. There's a max there. So here you got a min. Here you got a max. And at 10, negative, positive. This will also end up being positive because you end up squaring it here. So what was that again? Let me make sure we're on the right track. Negative, positive, positive. So it's negative. So at 6, we got neither. Nothing. So you have a minimum at x equals 0 of f of 0, which you can plug that in. That would end up giving you 0. And you have a maximum at x equals 4 of f of 4, which we'd have to plug in Again, here would be my cheat answer. It'd be 4 to the 2/3 power times 6 minus 4 to the 1/3 power. And I can make that look pretty if I wanted to, but I don't feel like it. There's my maximum. All right, hope that makes sense as far as how that goes. So that is your first derivative test, helping us here where the second derivative test didn't give us any help. Let me just show you really quickly. And what I would personally do, just trying to log on to my computer, I went in, take a look at this guy, and there's the actual function on Desmos just to make sure. So there's my minimum, there's my maximum, and notice here there's nothing at 6. So hopefully that makes sense, and we're going to leave it at that. Have a good day.